So today we will do stochastic DP. So we will formulate the problem, but why do we do stochastic DP? So we can go ahead with some applications again. So if we want to do inventory management, then the problem is to determine how many units to order and to meet the demand, right? And how much to hold and so on. So here there is a stochastic component because the demand varies probabilistically based on historical data. Now it could be let's say some event, okay, some festivals, and around that time there is a spike in the demand, and that there is a some amount of uncertainty how much demand will be there depending on the festival or event. So in these cases we will see what to do, how to handle stochasticity. Then we can have robot path planning again. So here the robot must move from start to goal and avoiding obstacles and uncertain terrain. Stochastic component here could be, let's say, sensor readings, which could be noisy, so one has to take into account terrains which may be a bit unpredictable, because you cannot really keep the terrain. I mean, you cannot expect the same terrain as during the test time, right? So while you are training, and what the type of terrain you will get during test time could be very unpredictable. So it should generalize to those kind of terrain. So in such cases, there are further things we will discuss, which is partial observable cases where the robot may not have the full view of the states, and that will be the case of POMDP. So we will also see those. Portfolio optimization is also comes under stochastic DP, because the asset prices and returns could be uncertain, because there could be some uncertain news, some political news that might affect the stock prices. Okay, so if you are into bitcoins, then you saw that the bitcoins valuations increased drastically once Trump won, right? So because he favors bitcoins. So depending on such events, stock prices might increase or it might decrease. So there are stochastic components there. And then in general, multi-arm bandit is another interesting area in itself. So here again, obviously the model itself assumes stochasticity. So we will see this a bit later. And resource allocation in cloud computing again. So we have a cloud, and depending on the resources, we are looking for what are the good ways to allocate resources so that the compute resources are used in optimal way, in the sense that there are not many idle nodes. So again, there is a stochastic component, because the demand for the compute resource could vary, and there could be uncertainty in those demands. So again, resource allocation in general could be modeled under SDP. So let us now formulate SDP. So we have seen dynamic program, but now we will look into a stochastic variant. So let us assume a perfect state case, state observation case. So now the new state that we get, which we call xt plus 1, is dependent on xk, uk, and also on wk, which we call random disturbance. Now this is the stochasticity we are talking about. Wk models the stochastic nature. So now again, depending on the problem that we saw, this w could be some physical noise. For example, the robot going through certain path encountered some noise in the sensor or things like that, or even the terrain uncertainty. It could be market uncertainties when you do portfolio optimization, and then spike in the inventory, or even unpredictable breakdowns could be assumed as some kind of disturbance. So just like DP, we can write down the cost function for stochastic DP. So starting from the terminal. So this is to terminate the job at the end stage. So there is no UK or WK involved. But then for the intermediate cases, we have the controls, but then those are also dependent on WK. So the state, given the state XK and UK, you may have different types of disturbances in WK. Okay. So overall GK will be a random variable because it depends on WK. So in the stochastic case, we will develop a new term which we call policy, although we have used policy before as well, but it is more relevant here. So here we say policy denoted by mu 0. So the set of these we denoted by pi. So at state 0, what was your policy? Policy is basically a way to produce the control, and using that control you will go to the next step. So we have used this before, but we are formally defining that here as well. So mu 0, mu 1 up to mu n minus 1, these are the policies at stage 0, stage 1 up to stage n minus 1. So mu k could be seen as a closed loop control law or a feedback policy, but then these things could be obtained via some simulations as well, we will see. So this specifies the control. As I said, mu k policy when acted on the current state xk gives me the control uk. So so we can use this mu k as some kind of a function that when applies to xk, it tells me the control to take for xk. So overall, this is the cost, total cost, assuming that you have gone through certain policy. So this policy itself is bound to change. Obviously, that's the part of learning that we will do in this course. So it could be some very base policy, and then you will keep improving on this and optimize the total cost. So in general, the total cost for a arbitrary pi policy could be written as the terminal cost plus the cost from n minus 1, n minus 2, and so on up to the 0. And here, instead of writing u control, we are saying the u control is obtained by applying policy mu k at state xk. So it's very similar. As you can see, there is no real difference compared to dp. We have added wk everywhere, and we have also, rather than writing u control uk, we have written this in this slightly different form. We write this as policy applied on xk produces the control uk. Okay, so as such, it's pretty much same as before. So this is the maths form. Basically, we have the cost defined, and given the problem and the policies assumed, we are supposed to minimize this. So the optimal cost function obviously will be the one for which this gets minimized, and the choices we have in hand are the controls. So basically, cost function is a function of the controls, or in general policy. So this is a minimization problem over the pi. Okay. Basically over the controls. Okay, so earlier we used to write minimize over control. We will say minimize over the policies. So overall, this is what we are trying to solve as an optimization problem. This is the problem we have in hand. It's a stochastic optimization problem now because you have wk here. And another change that you see from the deterministic case is that we have expectation here. Okay, so previously we didn't have this expectation term. So since this is a random variable, we can talk about some statistical estimates, like for example mean. In this case, we are looking at the average value of the cost. So mean is possible to take. So in the cost, you will now see expected value. Okay, so basically this is about stochastic dp form, and the policy for which we will solve this optimization problem, the minimization problem, we will denote it as pi star, which is quite standard in optimization literature to write a star for the optimal value. So pi star will be the policy that minimizes this cost. Okay, so just like in exact dp, we had two steps. We had first we computed optimal cost j star, and then once we had and usually we did it from the terminal like jn, and then we go to n minus 1, the tail sub problem, then n minus 2 until the end tail sub problem, and so on. So that's one way. So if we do that, and then we have the second stage is finding out the policy. So basically, policy, once j stars are known, policy is easy. So I can go forward. I can start from x naught, and I will see for which u naught the minimum cost is achieved, because I know the minimum j star. So that way I will keep producing the optimal u0 star, u1 star, and so on. So that was a two-step process. Once we know the cost, we know which controls would have produced such optimal cost. And same way we can write this in two-step also for SDP. We can do the cost computations first and then produce the optimal policy. So everything remains the same basically. So you find out so you start from the terminal jn xn. So let's say this is your optimal cost, and then you go to the tail sub problems, n minus 1 solve the tail sub problem, and then n minus 2 until the n, and so on. So this is very similar to DP. The only difference now you see is in the stochastic case you have a random variable wk, and then you have the expected value, because that's what we can do in the random variable case. So then and then finally we get the total cost J0 star. So so basically we have to solve this optimization problem just like in the exact DP. We can solve it backwards, but only difference is it's stochastic. So similarly, and once we know this J naught star, we can get the optimal policy mu k star. So optimal policy again, once we know this J star from the previous cost calculations, we can start producing the optimal control or the policy, whatever you want to say. So in this case, we will get these optimal controls, and that's when we can say that we have kind of solved the problem. So, and then just like in exact DP, we can also go for the approximate stochastic DP. So in that case, we will replace this exact optimal cost by some approximate cost J tilde k that we also saw in the exact DP. So what are the complexities involved when we work with stochastic DP? Now we can, I will explain this with
it's super simple, and so I'm just gonna start to play it and talk through it as I go. So you're playing in this middle here, and these pieces are coming down, and I'm able to make them go left, I'm able to make them go right, and what you're doing is you're stacking them and trying to create horizontal lines on the bottom. It's very simple. So I've created that. Now you are able to sort of turn the things around to help make a shape. As you can see, I'm doing that. You also can still move them left and right. Now once they come down, you can speed up the coming down, but you cannot go back up. So what you want to start to think about is how can I place all these things to create lines. Maybe I'll put this one like this and clear that line. And here's another one. Maybe I'll put it like this, bring it down, and there isn't much more to the game than this.
Where there is some stochastic, so it will be in that category. So if we look into the Tetris game, again we have the states would be the number of the blocks here filled here. So if you have played this game before, then you know what this is about. So these blocks keep coming from the top, and then you need to place them at the bottom. And the goal is to complete one row. You place these blocks in such a way, and you are allowed to move these blocks and also rotate these blocks. And if you fail one row, then you get a score. So you will see a score here. And basically the number of lines you fill, and the score will keep increasing. So this is about the Tetris game. So here the current block is this we call it I block, but it's rotated by 90 degree. So this is a I block, which you may apply the control, and it may rotate by 90 degree, and it can become like a vertical block. So those are the things you are allowed to do, and then you can move this block horizontally using the arrow keys right and left. So these are part of the controls that you're supposed to take, and then you will place them in, now the bottom row is empty, so you can place them wherever you want in this case. And then in this game, usually you are shown the next block to come. So next block that will follow is this one. But what is important to note is that you don't know the third block that will come or the fourth block that will come. So those blocks are kind of random. Which one will be the third block is something you don't know. And the block might repeat. So maybe you might get this block again. It's also possible. So there is a randomness there as in this. So this is how the game happens. So I put the I block here, and then the new block came, and then the next block to come is this T block. So this is the L block. So again, I will try to put this somewhere. So let us say I put it here after rotating, and then the T block that came, I will try to put it here. And as you can see, once I put this here, one row will complete, and ideally I should see an increase in the score. So if I do that, then you see the row got completed. So basically when this gets completed, the whole row disappears, and what is left are the other blocks above which are not completed. So this block and this yellow block will remain. So this block and yellow block remains, and then the next block comes, and then you put them in place, and then you think about the next block that is supposed to come. So this way, if you keep playing, then this block came, you put it here, and then this block came, you are going to, let's say, put it here, and then the next block is coming, and you will think of putting it somewhere. Ideally, your goal is to fill a row, whichever row, it could be bottom row or even the top row. So this is how the game goes, and then you get a score. So previously, we completed one row and we got a score of 40. So the cost here could be seen as negative. So as such, for us, the cost, that the way we formulate the math, is the cost is like we want to minimize. But then the way this game is formulated, my goal is to increase the reward. So I can take cost to be negative of the reward. Okay, so just to fix this in my maths, right? So the cost will be for us is the negative of the reward that I'm going to get. So states as such could be you may use a XY coordinate system. I mean the grid point, and you can say which of the grid points are filled. You put a 1 there, and which of the grid points are empty. So that could represent the current state. So in the current state, in this, you can think of 1 here, 1 here. So this is, let's say, 0, 0 point. This is 0, 1 point, and this is 0, 2 point. So here you can put 1, 1. You can declare a matrix, and then the weights are, and you can put which of the entries are filled. So that will be your current state, and then the blocks that you see are the observations. I mean, these are the blocks that you see, and then you are supposed to take actions based on that. So or the controls. So the control that you will take will be, you are allowed to kind of rotate and move it left or right, and then finally place it somewhere at the bottom. So all this is part of the control. All the things that you did to go to next state. So next state will be where it will be fixed. So let's say I fixed it here. So this is my next state. And to bring this guy to the next state, whatever things I did, that will all be part of the control. Okay, so it could be a vector. You could be a vector which I took, and then I had to place it here. But then if I have to model the stochastic uncertainty here, because the block that will come next is not really kind of deterministic. It might repeat with some probability, or it might change, or some blocks will have very less probability, or things like that. So in my model, I need to have I need to assume that my control is dependent on these random disturbances W. So when I do the cost computation, then the real challenge when I do cost computation is to compute this expected cost. So in this case, the expected cost, because for the same state, there was a chance that I could have got some other block, and hence my U would change. So basically, to do a cost computation here, I should have considered a sample mean of the cost. So sample mean would be, given the current state xk, I will generate various uk, and then look at the average cost that I get, and these and I also change these blocks in my sample. So in the same state, this block and the cost calculation, and then the another block cost calculation. So that will give me an average estimate of what could be a good control. Again, these choices may kind of be quite large, because the state itself can be quite large. So the fact that I am in this state, there could be many possibilities of this state. Okay, so if I see this as a grid of let's say so it's 10 by 20, let's say 10 by 20 grid. I don't know like how many, maybe there are 30 grids in the y-axis and 10 here. So maybe let's say 300 grid points are there. So 300 grid points are there, then the possibilities that you have is so many, right? Because you have one, or you can have 1 or 0 at each point. Okay, so then you have, for 300 grid points, you have 1 or 0, 1 or 0. So it's like 2 300 times, right? So 2 to the 300, right? If I'm not wrong, 2 to the 300 possibilities of states, which is quite huge, right? Because each block I have 1 or 0 possibility, 2 possibilities, and there are 300. So 2 times 2 times 2, 300 times 2 to the 300. So there are 2 to the 300 states here, and for each state, I have these blocks that might show up at each state. Each of those 2 to the 300 states, one of these blocks can show up, and then these blocks can also show up randomly because this could have shown up in the same state, or some other block. There are 7 possible blocks in Tetris, so any of the 7 could have shown up in one state itself. So 2 to the 300 times then the number of possibilities you have is 7. So each of those could encounter 7 of those. So so the way to compute the cost here would be, obviously you will not be able to go through all the states. 2 to the 300 more than the number of atoms in the universe, so you cannot really do that. So So then you will go ahead and ask, do I really need all the details of the state, or was this, so when I'm playing this game, do I really need all the explicit details of the state, where it is filled, where it is not? Or when I'm playing this game, my mind is only looking at some important features of this state. So in other words, is the explicit state which is important here, or some features of the state which actually is important to solve this problem? So from going from this huge state space, which is 2 to the 300, we need to think about a way to first reduce this state space. That itself, reduced one, may itself be very very big, but certainly we need to do that. So one possibility is to understand what is really important in these states, in this game. What really matters in this game? Are explicit details which matters, or just some idea about the gaps we have in the rows, and maybe the relative height of these columns, or which is the tallest column? Okay, so which are the features which are enough from the state to the feature space, and then this feature space is what I need to now decide on the actions or the control I will take. Okay, so there could be one additional step that we would like to do here, is to extract interesting features, reduce the space there, and then based on the features we will say, okay, now for those becomes my new kind of state, the features become my state, and then based on that I will decide which step of controls I can take. But again, features we extracted, that's like another thing. So we will cover those things in detail as well, how to extract features, which is really required in this. So if a robot is going around in a terrain, then you really could not explicitly store the pixel values of everything that the robot sees, but rather the robot should be able to understand the features of the terrain. So there is some tree out there, there is some pit out there, so there is some person out there, not in the explicit detail. The pixel space is even bigger. Okay, so clearly we will go into the pixel space. That itself is a big problem here, and then due to the stochastic nature of the problem, we need to do some simulations that gives us the expected cost, and simulations are needed to compute the sample mean, because I don't know the distribution with which these I don't know the distribution of W. So W is in our model. I don't know the distribution W according to which these blocks are generated. So what we are really looking for is the distribution P, which so it could be conditional distribution P, xk, uk, and then what is the expected, what is the block that is going to be sampled given xk, uk. This is not told to us. In fact, this is why this game could be fun, because what is the third block? In this case, the second block is shown to you, but to make it interesting, even this may not be shown to you. So you just see this, you fix this, and then some block comes as next thing. You don't even know what will be the next ones. Okay, obviously you don't know the third one, but let's say to make it interesting, even the second one is not known. You fix this, and then something comes, and then at that moment you're supposed to decide what is the optimal control to put it, so that you may have the immediate reward to fill a row, or maybe in next 2-3 steps you will see the reward of filling one row. Okay, so there will be some randomness, because we don't know which block will come next, and in which frequency they will come, and so on, obviously. So when we are in that kind of situation where we don't know, then we are supposed to kind of work with sample mean. Okay, so if you want to do exit poll, then you are not going to ask everyone in the population about who they voted for. These exit polls are based on some small sample. Okay, so you go around, hopefully your sample is a good one. Now how you do sampling itself is a big deal, but you go around and maybe you go to diverse population and then take the sample, and based on that sample you compute the mean. Okay, and this is what we're supposed to do, because I really don't know the distribution of which I really don't know the distribution for which I can say the person, I mean, overall this is what should be the exact mean. So exact mean computation is not in our hand. So we can go for estimated mean, which is like sample mean. So now how do I compute the sample? Basically, for a given state, I will see this block, but then I will say, okay, what if the other block was there in this state? And then I play along with those, look at the final cost, and then take an average of that. So the average is over the various samples I took. unlike the exact DP, the deterministic case, where we took these controls and then we explored the controls in the future, and then we took to the accumulated cost. But here, for the given state itself, there could be randomness there, and this affects the control. So I'm supposed to do the sample mean in this case. So so this will be. So this is so is Tetris a sequential decision making problem? Obviously it is a sequential decision making problem. And is this a stochastic game? Obviously, because the blocks can come in different shapes. Again, is this a finite horizon case? As such, it's not a finite horizon case, because you can keep playing as long as you have space, and none of this tallest block doesn't touch the roof. So as long as it doesn't do that, the game keeps going on. Okay, so this is also an example of infinite horizon, but if you want to put some timer, then obviously then it becomes finite horizon. So it's an infinite horizon stochastic DP example. Now we will see a solution for this in a bit more detail once we develop more tools. But for the moment, you can see an example of a stochastic case where the cost approximation will be over some samples. Okay, so these are the things you have to do. So optimal policy for Tetris. So optimal policy, as I said, what I said is just described here. So basically, how do we estimate the cost? So we need to do the sample mean for a fixed xk and various samples uk. Okay, so these with those where wk is a way it helps you to kind of get those samples. So we have to estimate these mean over some samples. Okay, in practice. So okay, so optimal policy we saw, and then we can write down the stochastic DP algorithm just like in the deterministic case. So we start with J star, and then for k equals to 0 to n minus 1, this is the optimal cost, and for which this minima is achieved, we call it the optimal policy. So that's basically the stochastic DP. Now Tetris was a complex case, and we are not going to solve that immediately, but we saw the difficulties. The difficulty we saw in Tetris was the large state space. We need to extract the features, and then there is a randomness involved. It's a stochastic nature. So once we develop some tools, we will try to solve that. But before we go there, we can solve a simpler example where it is possible to explicitly solve the stochastic DP case. So let us go through some smaller, easier example. So here this is called a linear quadratic optimal control. So this is a problem coming from control theory. Those who work in robotics primarily use control. So this is one possible model. Let's say we consider the linear system, in the sense that the new state that is produced kind of linearly from xk and uk and wk. So xk was our state, and control was uk, and wk is the disturbance that we have. So this is one possible model, how the new states are produced from the old states. So this is, and then what would be our cost model? So cost, in this case, we write this cost in this form. So again, this cost is dependent on the problem that we are going to solve. In this case, it's a linear control and quadratic cost problem. So that's how we decided the cost to be like that, because this makes sense for this problem. But cost could be different for different problem depending on the problem we solve. So here we have this this quadratic cost that we assume. This is assumed to be of this form, and then Q and R are some weighting parameters here, and which are constants. And then we assume no constraints on xk and uk. So we are not assuming any constraint, but in practice there could be a constraint on the type of control you are going to take or the states you are going to go. So that will be the case of the constraint case. We will see those cases later. So cruise control is one possible example. So many of the cars that you will see have this cruise control feature here, right? Adaptive cruise control here. So this is like when you go in a highway, and then it's a long distance expressway, and then you don't want to kind of put your foot on the accelerator continuously, then you may put you may switch on some button there, and then you can set the speed that you want the car to go, and then you can put your foot off the accelerator, and then it will try to manage the constant speed or the average speed of 70 km/h, let's say. So this can be a big relief, the adaptive cruise control, and the linear quality control could be used for this problem. So let us try to solve this fully. So cruise control problem, where we consider a vehicle that moves on a straight line road. So straight line in the quotes basically, okay, because if we don't consider straight line, then there is an additional thing that you have to see is the steering wheel. So that will complicate the model for us, because we also have to the control will also involve the degree of rotation of the steering wheel. So for the moment we keep it simple. We assume that the road is straight. Okay, so and then under the influence of the force UK. So the force here refers to the gas that you're going to kind of apply basically. So or the accelerator that you want to apply to maintain a constant speed. So this is what we call it force, but this force will produce it will be proportional to the speed that you will obtain while applying the force. Force will depend on the weight of the car. So this force will be multiplied with the B parameter, which accounts for the weight of the car. More the weight of the car, more the force is required to increase the speed. So with that in mind, and we are assuming that it's a kind of a constant friction throughout, or not too much influence of the friction right now. So the objective is to maintain the vehicle's velocity at a constant level v. So the velocity that we want to maintain the cruise speed is v. Okay. And then the velocity dynamics for these would be the velocity vk at time k after the discretization and applying the Newtonian dynamics and all. We can write down in this the vk plus 1 that we get will be old vk plus the force that we will apply, and the b will be the parameter that will kind of make the units in the velocity units. So basically we will divide by I guess the weight and multiply by I guess g. So this will be kind of fixed for the weight of the car, and the g will be the kind of the fixed, the gravitational constant, and so the basically it depends on the force. So more the force, the more the proportional velocity, which will be given by b uk. So and then we can say that these controls are applied in unit time everywhere. So assuming that b uk is indeed the proportional velocity that we will get out of that, and then the disturbance that we have is the wk, that could be some general disturbance. It could be some wind, some wind coming from the opposite direction that's slowing down the car, and so on. So again, the nature of the disturbance also is kind of important. To simplify, we can say it's a zero mean plus some variance kind of a disturbance, to simplify. But if not, then yeah, so there will be a mean there as well. So what we are saying in this model is wk is a stochastic disturbance with zero mean and a given variance sigma square. Okay, so this is a noise, but a specific kind of noise with zero mean and variance sigma square. Then we can reformulate this in terms of our notations, which is state, action, and disturbance. So our state could be rewritten in this form. So this is a velocity equation, but then we can write this as state. So which we define as vk minus v. Okay, so state will be vk minus v. So basically vk is our current speed, and v is the desired speed that we want to achieve. So ideally we want xk to reach to be 0 throughout. So this is the state that we want to maintain, and so this is basically xk will be the deviation between the vehicle's velocity vk at time k from the desired level v. So if we substitute xk equals to vk minus v throughout, then we subtract v on the above equations, then it's vk plus 1 minus v is xk plus 1, and the right hand side also vk minus v is xk, and the remaining are the same. Now b, as I said, it could be the weight of the car, and it could even model some road condition, things like that. It depends. So we keep the b as it is for the moment, a constant, which when applied to the force produces the required velocity. So this is our state equation. So our new state is obtained from the old state and the control in this way. So you can think of these as those current cost function g xk uk, and so this is our g xk uk wk that produces xk plus 1. Okay, so so obviously the cost function will be to keep xk near 0 with a relatively little force. So that will be our cost. So we can write down this more explicitly. So we will apply the DP algorithm to derive the optimal cost to go functions. As I said before, the way the cruise control, the cost, this is a form of linear quadratic control. So our cost is like this. Okay, this is what we feel. So this comes from the modeling parts. Like for this, this is a good cost to take. Okay, so in a linear quadratic control, this is a good cost to take. And the terminal cost, as you can see, is like this, qxn square. So our jn, the terminal cost will be qxn square. And for the kth one, these are the ones, right? So that's why you see qxn square as the so jn star xn will be qxn square. That's the terminal cost. And then for the case step, we apply the DP form. So for n-1, let's say, so we know n, and then for n-1, we can we have this optimization problem. So basically, for n-1, we have the current cost at n-1, and then the remaining cost that we have from n-1 onwards. So then for n-1, we have this g of x and un, so which is written here, and then the remaining cost is this. Okay, so so then we expand this, and j star of this, we know that the cost of this is a quadratic cost. So basically, if we put this guy here, then we have axn minus 1. So I can do it here. So we have this quadratic cost, and then jn star xn minus 1 is the current cost, which is qxn minus 1 square plus ru n minus 1 square, and then plus j star this term, right? So the j is a quadratic cost, so we will put this whole thing here, and if we do that, so the first term remains the same as it is, like this here, and then the remaining, if we put there, then it is like qx, and in place of xn square, we have these guys here. So we have q a this whole thing squared. So this is a minimization problem in un minus 1. So we do some simplifications here. So basically we have q, so this guy remains the same, and then we take q common. Yeah, basically we expand this term here. So we expand this. So you take this as a, and you take this as b. Then apply a plus b whole square formula. So then we have a square plus 2ab plus b square. Okay, so this is what we did. The q was outside anyway, and then we took the expectation inside. So when we took the expectation inside, then w expectation is with respect to w. Okay, so these expectations, because expectation is only with respect to the random variable, so the random variable, wherever it is, the expectation will apply only there. So in this case, we can see that the expectation only is applied here, because you have wn minus 1 involved here, and then expectation is applied here. These guys don't have anything to do with w, so it skipped those for expectation calculation. Okay, so now according to our assumption, w is a random variable with 0 mean and variance sigma square. So for 0 mean, expectation of wn minus 1 will be 0. So that we are going to use here. So we have this guy, expectation of wn minus 1 will be 0. So because of this guy, this whole term will be 0. So the whole term goes away. Now the variance is sigma square, right? So hence this guy is sigma square, right? So using these, we have the simplifications, and taking out the terms that do not depend on un minus 1. Okay, so after simplification, we have these guys, which are right here, and then Yeah, so this guy q, which is right here, okay, there was a little bit, not the whole thing. Okay, let me do it again. So the way we did was qxn minus 1 square, this guy, and this guy, okay, came. So let me clear this. Okay, so this guy qxn minus 1 came here, and this guy came here. Okay, expectation wn minus 1 square is sigma square, and then the remaining one, which is the remaining one is ru square n minus 1 is here, and then this term is here. Okay, so we did this simplification, and we know that minimization is only with respect to the control, so un minus 1, right? So this is minimization. We are trying to solve the n minus 1 problem, so this is minimization with un minus 1. So minimization, so un minus 1 is only here, right, in these terms. So that's why minimization is only here. These terms don't have n minus un minus 1, so no need to minimize this. It's like a constant, it comes out. So now we are left with this minimization term. Okay, so how we can minimize this? If you have done some basic optimization thing, then this is a minimization problem in un minus 1, right? So this is of the form, we can write this as some constant x square plus q a so this is also like some constant plus b x square. Okay, so this is like minimization in x. I have put everything like x as a constant, r also as a constant, so basically things that don't matter, I could have put everything as a constant basically. So if you want, I can put everything as a constant just to be sure that what we want to minimize, right? So so I'm looking here, right? So this is the minimization problem. So c1 x square plus some constant times, so basically some constant times another some constant plus constant times x squared. Okay, so this is basically what we are looking at, is these variables x. In our case, the variable is un minus 1 here. So this is a simple optimization problem. If you can recall that it is a quadratic optimization problem, quadratic and very likely convex also. You take a double derivative and see if it is greater than 0. Then by second order derivative test, we know that it's convex. So the minima will be global minima, right? So so the convex are like this, right? So if a function is known to be convex, then the minima will be global minima, because it's like of this shape, right? So any minima you find will be a global minima. So what we are trying to claim here is that this function that you see here is convex. Now to prove convex, we can take double derivative and prove that it's greater than 0. So this is the simplified cost function that we took from the previous slide, like here. So we just copied this again, and so this is what we are supposed to do. So this is a small optimization problem, and this is a quadratic convex optimization problem that we are supposed to minimize. The expression minimized over un minus 1 in the preceding equation is convex and quadratic in un minus 1. Okay, so so this if you take a double derivative of this, what will be the double derivative of this, right? So this is like, if I take the first derivative of this, so, and this is with respect to n minus 1, right? So let us say this is my this is some cost p, okay, this total thing. So we could do dp by du n minus 1. So we are taking derivative with respect to n minus 1, right? This 2r u n minus 1, agree? The derivative of the first term, this guy, is 2r n minus 1 plus the derivative of this guy. The derivative of this guy will be 2q a x n minus 1 plus b u n minus 1. So the 2 went away, and then by chain rule we have to now take the derivative of the inside term, which I believe will be just b. Now let us simplify this and put everything in un minus 1, because we are supposed to take double derivative to check convexity. So I will take un minus 1 common, and this is 2r plus n minus 1 is like 2q b square, 2q b square, right? So this goes with n minus 1, and then the plus, the remaining term is independent of un minus 1. So this is 2q a x n minus 1. So this simplification will help me locate where is un minus 1, and then we can go ahead with the one more derivative. So this is d2 p by. So after doing derivative of this guy comes out, because this is like a constant. So this is like 2r plus 2q b square, and this is a constant. So this derivative will be 0 with respect to n minus 1. Okay. So this is positive because q was assumed to be positive, r was assumed to be positive, and b square is positive. So overall this is positive, right? So this is positive. So the second derivative test, from second derivative test, p as a function of un minus 1 is convex. This implies any minima is a global minima. This is a quick revision of those who don't do optimization. I'm not assuming that, right? But this is like very basic things, right, from optimization. So we have proved that this is convex, and hence if I do a minima, because in general if it's not convex, then any minima is not necessarily a global minima, right? So this is a minima, right? Any local minima is not a global minima, right? Now this minima is not a global minima, this minima is not a global minima. So this is not convex. But the fact that we prove that it's convex, this means that this is always of this shape, meaning any minima is bound to be global minima. So I'm like done. I will just look at the case where the gradient becomes flat. That's how we find the minimum. Now gradient becoming flat could be here, 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 right? But since this is convex, this is like the case where it will be flat at one of these local minima, and that is good enough. So gradient becoming flat is like same thing as saying that take the gradient and equate to 0. So setting the derivative to 0, right? So we did a quick revision of the optimization thing here. Okay. So we computed this this first derivative already. So that derivation we did, right? So first derivative is this. This is exactly is being used, and we equate that to 0. So we equate that to 0 here, and now we solve for the control, because it's an optimization problem in the control. It's a minimization problem in the control. So we will solve the un minus 1, and if you solve the un minus 1, so after doing some simplification, basically first step it will be to take common un minus 1. So we take common un minus 1, then you will get these terms as common, and 2 gets cancelled throughout. So it's easy to see that a un minus 1 after solving will be given like this. Okay. So don't see this as like additional term that came. I just put it there, okay? Because we are saying that u depends on the policy depends on, basically we solve for u, but then as according to our notation u comes from the policy, applying the policy. So you should be familiar with this. So un minus 1 applied on xn minus 1 is the u n minus 1. So we are solving for un minus 1. So overall this is un minus 1, but then we wrote it in terms of policy. So this was actually un minus 1 star, but then we wrote it like policy mu star n minus 1 applied on xn minus 1. Okay, just to clarify the notation. So basically we solve for un minus 1 star, which from here and we got this. It's just easy algebra here. So for this problem, the cruise control problem, what we saw is for the given cost, which is quadratic, what we saw is that it is explicitly possible to solve this control. So the next control that I'm going to take, the optimal control, is given by this expression. So here a, b, q, r are known, xn minus 1 is known, where you are at the state xn minus 1 is known, then the control, optimal control to take is now known. So these are some of the rare problems where I can have a closed form solution for control and the cost. And unlike Tetris, where we will never be able to write closed form like this, it's so complex, right? So then we substitute this guy in the equation here. So what we found is the optimal policy, but then we are looking for the optimal cost. So obviously we will substitute this this everywhere wherever we had un minus 1. So wherever we had un minus 1, we this is nothing but un minus 1. So we substitute this this expression un minus 1 everywhere we have, and then see what we get. So substituting this expression in this star, we obtain a straightforward calculation. So then you do that simplification, and then jn minus 1 star xn minus 1 will come out to be kn minus 1 xn minus 1 square plus q sigma square. Okay, so these are simple calculations that I might leave it up to you. You just substitute this, and then you remove the minima, obviously, because you solve this minima problem. So once you solve this, you substitute there, then no need to put minima, right? You minimized already. So okay, so then you get the cost expression, which is kn minus 1 xn minus 1 square plus this, where k is this. Okay, so we have used these constants and combined those in one place, and we call it like kn minus 1. Okay, to write this in a simple form. So what we get as a cost at n minus 1 is this nice recurrence we get. And at the nth step, our cost was this guy. Now recursively we go to the n minus 1 subproblem, and we solve the n minus 1 subproblem. We are lucky in this case to solve the n minus 1 subproblem to get to this cost at n minus 1. Okay, and now the question is, now can we do it for n minus 2? So recursively it will be similar expression. Okay, so by induction you can say, okay, for n minus 2 also will have similar expression, and so on. So this there will be, each time there will be this additional factor that will be coming in. So from recursion, can you now guess what will be n minus 2, and so on, right? So so the DP algorithm will require us to compute this until J0. That will be the total cost. So we can now continue the DP algorithm to obtain Jn minus 2 star from Jn minus 1 star, and the important observation is that Jn minus 1 star is quadratic. So Jn minus 1 star still remains quadratic with some this term that we have. Okay, otherwise it is like a quadratic plus q sigma square. Okay, so this is essentially quadratic plus some inconsequential constant term. So with a similar calculation, we can formulate optimal policy for n minus 2 subproblem and the optimal cost for n minus 2 subproblem in closed form as a linear and a quadratic function of xn minus 2. And so basically this, we can see this as some constant, and this is the quadratic term. So this process can be continued backwards, and it can be verified by induction that for all k, we obtain the optimal policy and the optimal cost to go function in the following form. Okay, so this is the kth step solution. Now how was the optimal policy at the n minus 1? Let us look at that. So this is how the policy looks like at n minus 1, right? So which is of the form this. So how is the policy dependent on the state? So this is of the form some L x n minus 1, where you can take L as this guy. This is a constant. So the policy is a linear in xn minus 1 with this L, and the cost is quadratic. So in the kth form, if we want to write, then policy we can write it like this: Lk xk uk, and L will be given like this. So why L is like this? So this is our L here, minus ABQ by R plus B square Q. Yeah, assuming that the Kn is defined to be Q. So if Kn we take it to be Q, then the Q will keep changing. So in this case, these guys. So yeah, it requires working through the kth step, doing some algebra and figuring this out in more detail. But I hope you can do this in the background as an exercise. So at the kth step, so these are the policies at the kth step, and these are the cost at the kth step. These have been simplified by doing some algebra, I would say. So maybe we can do this in the background as an assignment. That would be better. It won't be complex, but maybe time consuming. So assuming that these things are okay, the jk could be simplified like this, and lk could be written like this, and where the k itself will follow this sequence. Okay, so previously, so kn was q, and kn minus 1 we derived before, which is this. Now we are trying to write down what would be the kk. Okay, the kth step k. So we can write down the kth step iterations and then solve for the optima at the kth step and so on. So this is the closed form solution for the quadratic control problem, where we have the closed form expression for the policy. We have found out the optimal policy at the kth step to take, and then the optimal cost at the kth step to take. Okay, so this is one of the problems where it is possible to solve the problem explicitly. Okay, and these are very rare cases where we will be able to solve this. And this is even the scalar case, where we can have a multidimensional case as well, right? So where x could be a vector and so on. Okay, controls could be a vector. So we have assumed a very simpler scalar case. So multidimensional case will be similar, and it is possible to have closed form expression in the multidimensional case as well. Okay, so so I will put this in assignment, the kth step. So remarks on the linear quadratic optimal control. The process by which we obtain an analytic solution is, in this example, is noteworthy because, as I said, this is one of the cases where we can explicitly do that. But in general, these are not easy to do, right? Because you will obtain these cost estimates via some approximations. So we already saw in the traveling salesman problem where we did some approximation of the cost using rollout. So in practice, we may have to do some rollouts and things like that. It's not, so for example, in chess or Tetris, it's not possible to get a closed form solution of the cost or the policy. So this is a special case, right? So a little thought while tracing the steps of the algorithm will convince the reader that what simplifies the solution is the quadratic nature. So one of the things that you can realize is the nature of the cost helped you in this case because it was of the quadratic form, and the linearity of the systems. So basically the policy, which was linear, that also helped you in this case, because that's when it became a quadratic and convex problem, which was easy to solve because take derivative equate to 0, minima was well defined. But in general, the cost itself may not be of that form. It may be more difficult cost. Quadratic may not be possible in all cases. And obviously the policy may not be linear. It could be highly nonlinear. So all this in real life cases we will find further in the course that these assumptions are really very convenient right now, but we won't be able to do these things in general. So it can be shown in generality that when the system is linear and the cost is quadratic, the optimal policy and cost to go functions are given by closed form expressions even for multidimensional case. So as I said, x, u, all these are multidimensional vectors, and even there we can have some closed form solution. Optimal policy is a linear function of the state that we have seen, and the optimal cost function is quadratic plus constant. In contrast, most DP problem encountered in practice require a computational solution. So that's what I said, that in practice we won't be able to have such nice closed form solutions, but we will go for simulations and so on. So in this case, we saw that what we saw in this example is also the effect of disturbance, right? So effect of disturbance was not that explicitly found in neither in the L policy, neither the this K is independent of the disturbance. So there is no sigma involved here anywhere when you are taking the policy, which is also seems like a simplified form, because in general our policy might be dependent on the random variable, but somehow we get to a case where policies are independent because mu k is lk xk and L does not involve any sigma. So this is also a simple case here, but we may not expect such things in future. So certainty equivalence. So optimal policy does not depend on the variance of Wk and remains unaffected when Wk is replaced by its mean, which is 0 in our example. This is known as certainty equivalence. So this is a special case where if the optimal policy does not depend on Wk, we call this certainty equivalence case. Now we have seen Q policy, which is really again very simple. In the it's just a notation thing here. So we have seen Q factors before, and we can do the same thing in the stochastic problem as well. So similar to the deterministic case, we can have Q factors in the stochastic case, and as we know, Q factor earlier were defined in deterministic case to be the current cost, and then the terminal cost. The only difference now is that we have Wk here, and then we have expectation with respect to Wk in the Q factor. So Q factor is about combining the current cost with the future cost. Combined, we call it the Q factor. So the optimal cost to go functions Jk star can be recovered from the optimal Q factors, obviously, because optimal cost could be found by minimizing the Q factors over the controls at the kth stage. Okay, so that gives me the cost approximation at the kth state. Now, so the DP algorithm could be written in terms of the Q factors in the stochastic case as well. Is the same thing. So we can write this as in terms of Q. So Q will be the expectation of this plus minima of the Q again. So these notations will be useful if we go to the Q learning part later on. So we have just these remarks. Again, for stochastic DP, the idea of approximation in the value space is similar. You replace Jk star by some cheaper variant like Jk tilde. So one of the principal RL methods to deal with difficulty is approximation in the value space. We can use Jk tilde in place of Jk star. So wherever we have Jk star, we replace it by Jk tilde. And now how we will approximate these? Again, one possibility we saw in the last class was rollout. So look ahead and roll out. That was one way to get J tilde. Here we can have similar ideas, but just that it is stochastic, and we may have to do some additional cost, additional average. We have to generate some samples for the random variable, and we take a average, and that will be the estimate of the cost that we are looking for in this case. So just like in the Tetris game, as I said, for the given state, you ideally want to have multiple samples and then combine average cost of that. So there is additional difficulty here that you have to compute the expectation over the variations in your control. These variations are random variations. So that's the additional step you need to take care of when you are working with the stochastic case. We will see some more examples in this case. And we can start infinite horizon in the next class. I will just take a minute to just close this. So infinite horizon is basically about when n, there is no capital N as such. It's like you keep generating the states, taking controls. It's a never-ending process. So how will you deal with those cases, right? Even Tetris game is a infinite horizon as such, because you can keep playing as long as you have space you can keep playing infinitely. So how do we formulate those problems? So those problems could be seen as a finite horizon where n going to infinity. So we can use the same notation as the finite horizon, but what are the changes now? So the changes that we see now is there is a limit, n tends to infinity. So from finite horizon we are going to infinite horizon, so why not take n tends to infinity? This is still the stochastic case, so we can we need to take the expectation over this w case, and then we can write down the cost like this, okay, which is really from k0 until the end, okay. And then there are some changes that you see in the cost like this, alpha to the k. We will motivate these things in future class, like why the cost needs to be kind of scaled by alpha k, and whether alpha k will increase or decrease as the k grows, right? So should I give more importance to the current reward and as k tends, because if I expand this, then it will be from 0, alpha to the 0, then alpha to the 1, then alpha to the 2, and so on. So in this sum, is it that I will give less importance to some of the terms as k grows? If alpha is between 0 and 1, then if k grows, then it's going towards 0. Now if alpha is close to 1, like 0.9, then it goes to 0 but slowly. If alpha is 0.1, then it goes to 0 very fast. So these could be the ways to see, okay, how my cost, because it's an infinite horizon problem, so we want to deal with some convergent series, not something which kind of like convergent in the sense like, yeah, it's it does not accumulate the same kind of reward throughout, because then it is like a never-ending sum. Okay, so there are different ways to kind of like formulate this. In this case, it's we can look at this discounted thing and then discounted reward setup. So here j pi x naught denotes the cost with the initial state x naught and the policy this, and alpha is a scalar in 0, 1. Okay, so this is a typical thing to put alpha between 0 and 1, and then depending on the problem you decide what could be the good alpha. The current cost is more important to you, or the past cost was more important to you. That helps you decide what could be the alpha. And the function g and f define the cost per stage, and the system equation is given by this. For the moment we assume that f is not changing from one step to the next. There is a function that for a given k produces some output, but the same function when applied on xk, uk, wk, which changes, let's say, then it produces a different output. So we are not saying that it is fk. We're not saying that fk is like same f, but depending on the state, it's a function that produces different states. So we can leave it here. We will start with infinite horizon in the next class, and we will set up the details, and the Bellman equations and so on will show up here. Okay then, so we will stop for today.